You probably think of the speed of light as just a number written in a textbook. A very large number, sure, but still just a number. About 300 million meters every second. Faster than anything you have ever seen. Faster than jets, rockets, or particles we smash together in labs. And you are told this is the ultimate limit. Nothing goes faster. End of story. But that explanation is strangely empty. Saying it's the limit because that's how the universe works does not really explain anything. It just restates the rule. If you stop and ask a very ordinary question, what is actually stopping you from going faster? You quickly realize that most people have never really asked it. They accept the rule because it has a famous name attached to it. Einstein said so. Physics says so. Move on. But if you take the question seriously, something unexpected happens. You discover that the speed of light is not just a very fast motion through space. It is tied to how space and time themselves are built. It is not just about how quickly something can move. It is about what motion even means. Once you see that, the idea of going faster does not feel forbidden. It feels undefined, like asking, what is north of the North Pole? To see why. It helps to begin somewhere completely familiar, long before light or relativity enters the picture. Start with falling. You have seen it your entire life. You drop something and it falls. Not sometimes, always, near the surface of the earth. Objects fall in a very predictable way. If you let go of something from rest, it falls about 16 feet in the first second. Galileo measured this centuries ago. It does not matter if it is a stone, a ball, or a book. The behavior is the same. This is ordinary experience, and it feels obvious. Now think about the moon. The moon goes around the earth in a steady path. It does not crash into us. It does not fly away. It just keeps circling. At first glance, that seems completely different from a falling object. Nothing about it looks like dropping a stone. But ask a simple question. If the moon were suddenly frozen in space, no sideways motion at all, what would happen? It would fall. Gravity would pull it straight toward the Earth. The only reason that does not happen is that the moon is moving sideways. It is moving forward along its path while gravity pulls it inward. Each moment, it is falling toward the Earth, but the Earth curves away beneath it. It keeps missing. That is what an orbit really is. Not balance, not suspension. Continuous falling combined with enough sideways motion to never hit the ground. This is where a remarkable idea enters. The moon is far away, about 240,000 miles from the center of the Earth. You are standing much closer, roughly 4,000 miles from that same center. That means the moon is about 60 times farther away than you are. Newton asked a careful question. What if gravity weakens with distance in a very specific way? What if doubling the distance makes gravity 4 times weaker, and tripling the distance makes it 9 times weaker? In other words, what if gravity fades with the square of the distance? If that idea is right, then gravity at the moon should be 60 squared times weaker than gravity at the Earth's surface. That is 3,600 times weaker. On Earth, an object dropped from rest falls 16 feet in the first second. So at the moon's distance, an object should fall 16 feet divided by 3,600 in the same amount of time. That is only a tiny fraction of an inch. A barely noticeable drop in 1 second. Newton worked through the numbers carefully. He calculated how much the moon should fall toward the Earth in 1 second. If gravity really followed this inverse square pattern, then he compared that prediction to how fast the moon actually curves in its orbit. They matched, not approximately, exactly within measurement limits of the time. This was not just fitting a curve to data. Newton took one fact measured on Earth, how fast things fall, and used it to predict the motion of an object hundreds of thousands of miles away. Two facts that had no obvious connection suddenly became part of the same story. The same rule governed apples and the moon. Once that connection was made, there was no way to unsee it. Gravity was no longer a local behavior. It was a universal one. Once that idea was in place, it did not stay confined to the moon. Newton pushed it further and asked a natural next question. If gravity really behaves this way everywhere, what kind of paths should planets follow as they move around the sun? Not guesses, not sketches, actual predictions. When he worked through the reasoning, the answer was very specific. The paths should not be perfect circles. LLIPSES. and that answer landed with quiet force. Astronomers had already measured planetary paths in detail. Kepler had done that work years earlier and had found that planets do, in fact, move in ellipses. But Kepler could only describe what he saw. He had no reason for it. Newton gave the reason. One simple rule about gravity explained falling objects, the moon's motion, and the exact shape of planetary orbits. Different problems. One explanation. You start to feel a pattern forming. Then something even more familiar fell into place. The tides. You have seen them all your life, whether at the ocean or on a chart. Water rises and falls in a steady rhythm. High tide, low tide, again and again. At first glance, the explanation seems straightforward. The moon pulls on the earth, water responds. End of story. But stop for a moment and ask a very ordinary question. If the moon is pulling the earth toward it, why is there not just one high tide each day on the side facing the moon? Instead, there are two, roughly 12 hours apart. One when the moon is overhead, and another when it is on the opposite side of the planet. That should make you pause. Why would water pile up on the far side, away from the moon? What exactly is being pulled, and how? People tried to answer this in different ways. Some said the earth was pulled out from under the water. Others said the water itself was pulled toward the moon. Both ideas contained part of the truth, but neither fully captured what was happening. Newton saw that the key was not the pull itself, but how that pull changes with distance. Gravity does not act equally everywhere. Water on the side of the earth facing the moon is slightly closer to it than the center of the earth is. That water feels a slightly stronger pull. On the far side, the water is farther away and feels a slightly weaker pull. The earth as a whole is pulled somewhere in between. Once you see this, the pattern becomes clear. One bulge forms where gravity pulls more strongly. Another forms where the pull is weaker, and the earth moves ahead of the water. Two bulges, two tides. Every day. There is another way to describe the same situation. The earth and moon do not behave like one object chasing another. They move together. Both circle around a shared center of mass, a point located inside the earth, but not at its center. As they orbit this point, different parts of the earth respond differently. Some regions are pulled slightly more inward, others lag slightly behind. However you choose to describe it, the result is the same. The tides follow directly from the same gravitational rule that governs falling objects and planetary motion. Once you accept that, many other things stop feeling mysterious. Why is the earth roughly round? Because gravity pulls matter inward from all directions. Why is it not a perfect sphere? Because the earth spins, and rotation slightly flings material outward near the equator until balance is reached. Why are the sun and the moon round as well? For the same reason. Gravity shapes large objects into spheres unless something interferes. As measurements improved, confidence in these ideas grew. But science does not stop at confidence. It tests. And the better the measurements became, the harder the test grew. One of the most demanding tests came from far beyond the Earth, from the moons of Jupiter. These moons orbit quickly and regularly. Their motions could be predicted in detail using Newton's laws. Astronomers tracked them carefully over long periods of time and compared what they saw to what the equations predicted. At first, the results were unsettling. Sometimes the moons appeared several minutes ahead of where they should be. Sometimes they lagged behind by the same amount. 8 minutes early, 8 minutes late. That is not a small error. That is the kind of discrepancy that makes you wonder whether something fundamental is wrong. Were the laws incomplete? Were the measurements flawed? Or was something else interfering? Then an odd pattern appeared. The timing errors were not random. When Jupiter was closer to the Earth, the moons seemed early. When Jupiter was farther away, they seemed late. The motions themselves had not changed. Only our view of them had. And that raised a quiet but profound question. What if the delay was not in the motion of the moons at all? What if it was in the time it took their light to reach us? Faced with that strange timing problem, one astronomer chose an unusual path. Instead of doubting gravity, he trusted it. He assumed Newton's law was doing exactly what it should. So if the predictions were right, but the observations were off, then something else had to be responsible. What if the moons were not early? The idea was simple, but radical for the time. Light does not arrive instantly. When you look at Jupiter's moons, You are not seeing them as they are right now. You are seeing them as they were when the light left them. That means every observation carries a built-in delay. When Jupiter is closer to Earth, that delay is shorter. When Jupiter is farther away, the delay is longer. Could that alone explain the missing minutes? Once that possibility was taken seriously, everything lined up. By accounting for how far the light had to travel, the timing errors vanish. The moons were never misbehaving. The clocks were never wrong. What changed was our understanding of light itself. By measuring how much earlier or later the moons appeared, it became possible to calculate how fast light was moving. Not with mirrors or laboratory tricks, but by watching distant worlds and trusting a law of gravity. This moment is worth sitting with. The speed of light was not discovered by chasing light. It was discovered by believing gravity. When something did not match expectation, the response was not to abandon a successful idea, but to ask what unseen process might be missing. What if light takes time? That single question opened an entirely new door, and the answer turned out to be yes. This is how progress in physics often works. A rule that is proven reliable becomes a tool. When reality refuses to fit, the mismatch points to something new. One law helps uncover another. Without a clear expectation for how Jupiter's moons should move, the delay in light would have gone unnoticed for much longer. There would have been nothing to compare against from that point on. Discoveries began to build on one another. Each insight sharpened the next. Each new measurement created new questions. What began with falling objects and orbiting moons turned into a cascade of understanding that has continued for centuries. This is not a series of isolated breakthroughs. It is a chain, stretching across time, still growing. But once the speed of light was known, something deeply unsettling became impossible to ignore. Light does not behave like other moving things. No matter how you measure it, no matter how fast you yourself are moving, its speed comes out the same, always. That alone should make you uneasy. Picture a simple situation. You are standing still. You turn on a flashlight. You measure how fast the light moves away from you. The result is a fixed number. Now imagine riding on a very fast train. You shine the same flashlight forward, in the direction the train is moving. What would you expect? Instinct says the light should move faster now. This is where common sense starts to protest. In everyday life, speed's added. Walk forward on a moving train and your speed increases. Throw a ball and it carries your motion with it. Light refuses to play by that rule. No matter how fast you chase it, it pulls away at exactly the same rate. Why should that be true? How can motion behave like this at all? What kind of universe allows one speed to remain fixed no matter who measures it? These are not technical questions. They are deeply ordinary ones. And answering them will force us to rethink what we mean by space, by time, and by motion itself. So, why does this happen at all? Why does light refuse to behave like everything else? The breakthrough came when someone stopped trying to force light into old ideas, and instead questioned the ideas themselves. What if the problem was not with light, but with how we think about space and time? That shift sounds small, but it changes everything. Even today, long after the math has been tested again and again, this idea still feels uncomfortable. It pushes directly against intuition. The key realization is this: space and time are not rigid backgrounds where events simply play out. They are not fixed stages. They are flexible. They respond. They stretch and adjust in very precise ways. And they do this so that one thing remains the same for everyone, everywhere: the speed of light. Instead of light changing its speed to match you, space and time change themselves. When you move faster, time does not behave the way you expect. Your clock does not tick at the same rate as a clock at rest. It ticks more slowly. Not because it is broken, not because it is malfunctioning, but because that is how time itself behaves for moving objects. At the same time, distances along your direction of motion shrink. the space ahead of you becomes slightly compressed. These are not visual tricks. They are not illusions caused by observation. They are real physical effects, measured repeatedly and confirmed in experiments. Pause and think about that. Time actually slows down. Space actually contracts. And they do so by exactly the amount needed so that everyone, no matter how fast they are moving, measures the same speed of light. This is not coincidence. It is not adjustment after the fact. It is built into how the universe works. The speed of light is not just another speed. It plays a deeper role. It sets the relationship between space and time themselves. And the story does not stop there. Try to push something faster and faster, closer and closer to the speed of light, and another strange effect appears. Each increase in speed becomes harder than the last. Not because your engine is weak, not because you run out of fuel, but because the object resists being accelerated more and more as its speed increases. As you add energy, the object responds less and less by gaining speed. Instead, its resistance to acceleration grows. Its inertia increases. Near the speed of light, this resistance becomes enormous. To reach the speed of light exactly would require an infinite amount of energy. Not a very large amount. Infinite. That makes it unreachable for anything that has mass. This is not a technical limitation. It is not a practical problem waiting for better engineering. It is a structural feature of spacetime itself. Light behaves differently because light does not have mass. Photons carry energy and momentum, but no mass at rest. Because of that, they are not slowed by this growing resistance. They do not approach the speed of light. They move at it. Always. They cannot go slower or faster. That speed is simply how they exist. Objects with mass can come extremely close, closer than intuition would ever suggest, but never quite arrived at this point. A natural question arises. Why is the universe built this way? Why should there be a maximum speed at all? The frustrating answer is that physics does not give a deeper reason beneath this structure. The speed of light is not a rule imposed from outside. It is not a speed limit added afterward. It is a consequence of how spacetime is put together. Space and time are not separate ingredients. They are interwoven into a single structure called spacetime. That structure has a geometry, and within that geometry is a fixed relationship between distance and duration. The speed of light is that relationship. It tells you how much space corresponds to how much time. Change your units and the number changes, but the relationship does not. Light is not special because it sets the limit. The limit exists because spacetime allows only a certain maximum rate at which cause an effect can propagate. Light happens to travel at that rate because it has no mass. If light did not exist at all, the same limit would still be there. It is a property of the universe. There is another way to picture this, not of light itself. In everyday life, you treat space and time as separate things. You move through space, time passes. Whether you move or not, they seem independent, but in reality, motion always involves both. You are always moving through spacetime. Always. If you are standing still in space, all of that motion goes into time. You move forward into the future as fast as possible, 1 second per second. But once you start moving through space, some of that motion is diverted away from time. You are now splitting your motion between space and time, and that means your movement through time slows down. The faster you move through space, the less motion is left for time. Push that idea to its limit. If you could move through space at the speed of light, there would be no motion left for time at all. Time would not advance for you. That boundary is not arbitrary. It is the point where space-time runs out of room to adjust. There is a hard limit hiding in all of this. If you kept moving faster through space, there would come a point where no motion would be left for time at all. Time would stop for you. That is not a metaphor. That is what the structure of space-time implies. This is why light does not age. Along its path, no time passes. Emission and absorption are separated by distance, but not by time. What would it even mean to go faster than that? How could you move with less than 0 time remaining? This limit is not just an idea on paper. It has been tested relentlessly. In particle accelerators, we push particles to speeds incredibly close to the speed of light. Each tiny increase becomes harder than the last, exactly as predicted. No surprises. No exceptions. You see the same effect above your head every day. High-energy particles strike Earth's atmosphere and create unstable particles that should decay long before reaching the ground. Yet many of them survive. Why? Because they are moving so fast that time runs slower for them. Experiments measure this directly. The numbers match. Even the technology you use depends on this. Satellites orbiting Earth experience time differently than clocks on the ground. Without correcting for that difference, navigation systems would fail within hours. So why is the speed of light the limit? Because spacetime allows only a maximum rate at which causes can lead to effects. That rate is not chosen. It is built in. This understanding did not appear all at once. It grew step by step, from falling objects to orbiting moons to light itself. Each discovery leaning on the last. The speed of light is not just a number. It is a clue. It tells you how the universe fits together. And the fact that we can uncover that structure carefully and honestly is what makes physics worth doing.